So today we start representation theory of semi-simple algebras, and a lot of things today will be generalization of what we've seen for SLN last semester. So some familiar things will arise. We will inherit notations from our previous lectures. In particular, we fix some semi-simple Lie algebra G. And we fix some Cartan subalgebra inside. And we fix, so then we have corresponding root system that we denote by R. And also on G we have invariant non-degenerate bilinear form. Invariant non-degenerate form. So all that we have from last times, and now let us consider representations of G. So if V is a representation of G, what does it mean? So first of all, it is some vector space, right? And we have homomorphism ρ from G to all linear transformations of V. So this is Lie algebra with commutator. This is abstract Lie algebra, and this is homomorphism of Lie algebra. So this is what it means to have representation. And of course, one important thing to introduce here is weights and weight subspaces. So our weights will be elements of H star. So for lambda from H star, so dual to H, define the following. So V of lambda is the following set. It is all vectors in V such that the eigenvectors of H, so H acting on V, gives me is a multiplication by number lambda of H, and this is for every H in the Cartan subalgebra. So, all right. So by definition, if V of lambda is not a zero vector space, so if this is not zero, then lambda is called a weight of V, and corresponding subspace V of lambda is weight subspace of weight lambda. So then V lambda weight subspace of weight lambda, and corresponding vectors in there are weight vectors again of weight lambda. We will say sometimes if we would like to stress what is the corresponding eigenvalues. Okay, so then another definition which we already had in seminars, but let's fix it in lectures as well. It is weight lattice. So weight lattice is the set which is defined as follows. So it's denoted, we'll denote it as P. These are all elements in H star such that, well, this number 2 lambda alpha over alpha alpha is integer for any root alpha. Yes. Okay, so this is actually a lattice because it has some basis, and it is like a, P, as we saw in seminars, is this. It is a model over integers, right, with basis omega i's, where I runs over all simple roots. And omega I is defined like this: 2 omega I alpha j over alpha j is delta ij. So reminder, again, we denote by alpha i's simple roots. Anyways, so usually lattice, in mathematics, lattice is something like this, with some vectors, with some bases. And here we have concrete bases, omega i's. These are also called fundamental weights. All right. Now we can formulate our first proposition. Let V be finite dimensional. Representation of G. Then V admits what's called weight decomposition. That is, so then we have the following decomposition. V is a direct sum of V over weight subspaces, where lambda is, well, we can run it through the whole H star, but I would like this proposition to say actually more. So this is some set P of V where P of V is some subset of P. So I claim two things here. First one is that V admits weight decomposition, so it is a direct sum of its weight subspaces. But then I also claim that the weights belong to weight lattice. Okay, so let's see this. Again, the approach to proving a lot of stuff here is to use representation theory of SL2. Since we have SL2 triples, this will give us like a lot of things. In particular, well, SL2 alpha, where for each root alpha, is a Lie subalgebra in G, right? So therefore, V is also representation of SL2 alpha. V is a representation of SL2 alpha, right? Where this is for any alpha in R. So V is finite dimensional, and we know that the element H of SL2 actually is diagonalizable in any finite dimensional presentation of SL2, right? So therefore, rho of H alpha, right, where rho is the corresponding homomorphism from G to endomorphisms. So let me maybe put it like this, a pair like this, rho V. So the image of H alpha is diagonalizable. And also all rho H alpha with rho H beta, they commute, right? Because Cartan subalgebra is commutative, right? And all H, so this is for any alpha and beta in R. So we have a bunch of linear operators that are diagonalizable and they commute. So therefore, we can, using linear algebra, we can simultaneously diagonalize them. And this is already means that V is decomposed as this is direct sum of weight subspaces. So let me call it, write it like this: rho of Gotic H, so the whole Cartan subalgebra. So remember also that H alphas form a basis in Cartan subalgebra, right? So therefore, this is simultaneously diagonalizable and therefore we have weight decomposition. We have decomposition. V is sum or lambda in P of V, V of lambda for some P of V in H star, right? So now we need to prove that P of V is actually belongs to weight lattice. Okay, so consider and of course we would like to right. We don't want to include in P of V any elements of H star such that V of lambda is 0, right? So therefore, P of V is by definition all lambda such that V of lambda is not 0. Okay. Right. Okay. Let me take some lambda in P of V. So let me take lambdas from P of V. Then lambda so if I consider this number, so this is some number, I claim that this is an SL2 alpha weight of SL2 alpha representation V. Right? So since I chose this, why is this? Since I chose this is from this set, okay, I said that this is actually the set of weights of V. I don't want to include anything more to here. Yes?
So in this you are doing it for SL2, right? SL2 comma alpha.
So what is, yes, so we're using that V is actually also a representation of each SL2 triple inside G.
And because I don't understand how then we can have an H alpha and H beta.
Yeah, so we're using different triple H every time.
Sorry, I didn't.
So you have H alpha, right? It is inside SL2 alpha, right? So you have SL2 alpha it has like E alpha, F alpha, and H alpha inside. This is a basis. And H beta is in some other. But for each root here, V is still a representation of it.
So this vector space V is like a direct sum of various SL2 representations?
No, it's not a direct sum though. It's just because this SL2s, they might be not so as this SL2 and this SL2 inside G might not be their sum might not be direct inside G. Yeah, so it's just if you have a the idea is here is simple. So if you have some algebra, Lie algebra, you have its representation, and if you have subalgebra inside, whatever subalgebra you take, you might take different. Then this representation is also a representation of subalgebra as well. And you don't want to care about all this direct sum stuff. So this is you might think about this like in your spare time, but here I actually using the very simple statement is that if I have subalgebra, then my initial representation is also a representation of subalgebra. Yes, and so I know that V is a representation of subalgebra. H alpha is diagonalizable there with some basis. And H beta is also diagonalizable, maybe with another basis. I don't know. I take some different subalgebra. But I know that if I have a bunch of linear operators which are diagonalizable, then it's the statement. It is a statement of linear algebra that I can find common bases that diagonalize them. Yeah. All right. So this is an SL2 alpha weight. So why is that? Well, since lambda is some weight of V, what does it mean? It means that by definition, it means if I take H alpha, act on V, right, then I will get lambda of H of alpha V. Right, so therefore this thing is an eigenvalue of H alpha. And from representation theory of SL2, we call this an SL2 weight. Also, we know that in finite dimensional representations of SL2, let us recall, all SL2 weights are integers. Okay, so it's always this picture, should keep in mind. So you start with some highest weight, lambda, and you go to negative lambda, but all this, and you go by step 2. Right, and so this lambda, and so lambda minus 2 and lambda minus 4, and so on, they should all be integers. So that's how representation tier of SL2 is. And so therefore this is integer. But then what is this? So by definition, this is exactly lambda. So I claim that this is exactly lambda h alpha, lambda alpha, sorry, divided by alpha alpha. Why is that? Because, well, I know that, so from which side should I do it better? So I know that lambda alpha, so this thing, so let me write it like this. Lambda alpha is lambda of h capital alpha. This was just our definition of h capital alpha. And then h small alpha was, so this is just parentheses, and h small alpha was I think, yes, 2h alpha over alpha alpha. So using all this, we get that this number is exactly this number. Okay, so therefore we proved, so this thing is integer, so therefore this is integer, right? And this is for any root alpha. So therefore, by definition of P, so these are all lambdas such that this is integer for any root of alpha. We know that lambda should belong to P. And so therefore P of V is inside P. So therefore lambda is inside P. So therefore P of V is inside P. Okay, so we proved the proposition. So next thing that we would like to discuss is that how weights of finite dimensional representations are related to while group. So I claim that actually, so let me formulate it here in the next proposition. So proposition again, so let V be finite dimensional representation of G. Then for any element of while group, we have, let me put it like this, dimension of V of lambda is the same as dimension of V of W of lambda. This is for each weight lambda of V. Okay, so let's prove this. So actually, the weights of V are they are symmetric with respect to W. So W acts on a set of weights of V. Moreover, dimensions of corresponding weight subspaces are respected by the action of W. Okay, so let's prove this. Of course, since while group is generated by simple reflections, it's enough to take this small w to be just one simple reflection. So enough to take w to be some simple reflection. But then again, my statement follows immediately from representation theory of SL2 because of this picture. So I claim that V of lambda is, well, let me write it like this. It's a weight subspace of V is a representation of SL2 alpha with some weight k. And what is this weight k? Well, this is, we also know that, computed this, maybe even not one time. So, of course, I would like, so since I restricted myself to simple reflection, I need to choose corresponding root here. So this is alpha I, corresponding simple root. So then this k is 2 lambda alpha I over alpha I. Right. So we actually computed it here, right? So this is this number. This number is the corresponding weight of SL2 alpha I weight of V is the representation of SL2 alpha I. So this is what? Lambda of H alpha I. But on the other hand, I claim that if I take Si and apply to lambda, this will be V weight subspace, again, of SL2, of V as a representation of SL2 alpha I, but I claim that I should put negative k here. Let's check this. Right, so what Si is doing, yes?
You have V lambda equal to Vk SL2 alpha I. What does the right hand side mean?
So this is how I denoted. So this k is not a G weight, it's a SL2 weight. So this superscript here means that I consider V now as a representation of SL2 alpha I, and this and the whole thing denotes the weight subspace of V as a representation of SL2 alpha I of this weight, of this SL2 weight. Okay? Right. So here I might also write G, right? So I have two algebras, right? G and SL2. And this is weight corresponding to G, this weight corresponding to SL2 alpha I. Okay, so let us check that these vectors from this space are exactly vectors of SL2 alpha I weight corresponding to this. So we need to remember what is Si of lambda. So this is, we take lambda and reflect it. So we subtract its projection to alpha I. And so what is the corresponding SL2 alpha I weight? So I need to check to take this and apply it to H alpha I, right? So this will be lambda of H alpha I. So this term minus, so this is some number, which is 2 lambda alpha I divided by alpha I. And then alpha I applied to H alpha I. Right? Then this is K, as we agreed. This is also K, right? Without this term, factor. And this is what? What is alpha of?
2.
Yes, this is 2. Right? Well, because again, alpha I of H alpha I. Let us use the same formula as here. Instead of lambda, you should take alpha I, right? So it will be 2 alpha I over alpha I. So this is 2. Again, this is computation that we did a couple of times. It's exactly the 2 that appears in SL2 when you commute H and E and H and F. Right? This is exactly the step 2 that we have all the time. And so therefore we have K minus 2K. So this is negative K. So exactly what we would like to see here. Right. So we actually, like, to be completely honest, we take some vector from here and checked that it has SL2 alpha I weight here, right? But well, you have weight decomposition, right? And so because of weight decomposition, we should have this equality. Because if this, so we proved inclusion, if inclusion is proper, again, the same technique, then, well, then we have a contradiction, right? So we have this, and therefore, but we know, again, from representation theory of SL2, right, that dimension, if we have a finite dimensional representation of SL2, and dimension of weight subspace corresponding to some mu, and to some to weights negative mu, they are the same, right? So therefore, dimension of V of Si of lambda is the same as dimension of V of lambda. Okay. So our next step will be to introduce highest weight representations. Okay, so let V be a representation of G. And let lambda be some weight of V. So now we don't require V to be finite dimensional. Okay. So let lambda be a weight of V. So by definition, some weight vector V of weight lambda is called singular if it is held by the upper triangular part n plus V equals to 0. So remember this triangular decomposition, n minus h and plus, right? So in SLN, n minus and n plus, they were lower and upper triangular matrices. So here n plus is direct sum of all g alphas such that alpha is positive root. So again, all this of course depends on the choice of polarization, but suppose, again, we I should have said that in the beginning, suppose we fix some polarization, right? And then we have this. Yeah, so weight decomposition doesn't depend on polarization, but what I call singular vector actually depends on polarization already. Okay. So next definition is that V is called a representation of highest weight lambda if well, there exists a singular vector V in V of lambda and okay, some technicality, of course. I don't want to call zero vector to be singular, right? So let me correct this definition a little bit and maybe write non-zero V here, right? So V is called representation of highest weight lambda if there exists a single vector V such that well, it generates the whole V. So let me write it like this. U of G applied to V is the whole representation V. So this is universal enveloping algebra, right? And so I start applying operators corresponding to the image of U of G in the morphisms of V, and by this I will get the whole V. So that's what I mean when I'm saying that V generates, this vector generates the whole representation. Okay, so so this is our definition. Now let us prove something about this. So first of all, let us justify the word highest weight vector. So we had singular, right? But I would like, so we also called it highest weight for some reason. So therefore, I would like to introduce some partial order on H star. But this partial order is motivated by the following lemma. So lemma it goes like this. So so consider, so let E alpha, F alpha, H alpha be an SL2 triple corresponding to some root alpha, Then we have the following. If I take E alpha and apply it to weight subspace of weight lambda, then I will end up in weight subspace corresponding to the weight lambda plus alpha. So E alpha is raising operator in some sense, right? It raises our weight by alpha. And similarly, F alpha, if I apply it to V lambda, it will belong to V lambda minus alpha. Okay, so this is just okay, proof is that this is straightforward check just using commutation relations in SL2. Using commutation relations. Very well. So let me not do this. It's this just completely the same check as we did in spring semester. We just we had some concrete vectors for alpha. So now our alpha is more abstract, and this is for any semi-simple algebras. Okay, so this motivates the following definition. So for lambda and mu, elements of H star, we write that lambda is greater or equal than mu if lambda is mu plus sum of positive positive roots, or I can say simple roots here. So alpha I are simple roots, I from 1 to R, where n i's are from, so these are non-negative integers. So for each I from 1 to R. So this is our definition of partial order on H star. So we compare two elements of H star by subtracting roots. Okay, well, simple roots actually. Okay, very well. So now, since we introduced this, let me now justify why this weight is called the highest weight. So next proposition is the following. Let L be a representation of highest weight lambda, and so then I claim the following two things. first it admits weight decomposition, and this weight decomposition is specific again. So it's a direct sum of L mu, where mu is comparable to lambda, first of all, in this partial order, and it's smaller or equal to lambda. And number 2, which actually directly follows from 1, is that lambda is a unique highest weight. I never actually fixed the term highest weight, right? So I said what is representation of highest weight lambda, right? But if I have a representation of highest weight lambda, then this lambda is called the highest weight of this representation V. Okay. So in number 2, I claim that if I have some other mu such that I have a singular vector of weight mu such that V is generated from this vector, then this mu equals to lambda. Okay, so that's some uniqueness. Okay, how to prove that? Well, this one will just follow from Poincaré-Bergov-Witt theorem. Okay, so does everybody remember what is? It was a long time ago in previous semester. So it said something about constructing a basis of universal enveloping of G, and actually we proved it for any finite dimensional Lie algebra G. Okay, well, so reminder on Poincaré-Bergov-Witt theorem. So it says that if x1, x2, and so on, xn is a basis in G, then x1 to some power k1, x2 to some power k2, xn to some power kn. So these things, right? So as k i's are some numbers greater or equal than 0, right? Is a basis in U of G. So this was Poincaré-Bergov-Witt theorem. So what's important here is that we order them. So if we have ordered basis, then monomials in monomials we should fix the order. Then this will give us a basis. But we will not need actually the part that these things are linearly independent, which is harder part of Poincaré-Bergov-Witt theorem. We will rather need that these things, they span U of G. So how do I do this? So by definition, so my V, it's a highest weight representation. So therefore, it's obtained, it's generated from V. Right? So therefore, it's like that. But then, by Poincare-Birkhoff-Witt theorem. So I have in my G n minus, h, and then n plus. So let me take this basis that first x1, x2, and so on will be from an n minus, right? Then next elements from this basis will be from h, and the last one from n plus. Okay. Then I can write it like this. So it's un minus un plus v. So each element in here can be written as monomials, where on the right I have only elements of n plus, in the middle elements of h, on the left elements of n minus. Okay, this is an easy part of Poincare-Birkhoff-Witt theorem. But then, so this thing. So remember, in universal enveloping, what it is? You start with so it's some algebra, right? Which has unit 1, right? And it is generated by elements of corresponding Lie algebra, right? So if you just loosely speaking think of it as polynomials, right, in elements of your algebra, right? Of course, it's not it, but so what's written here is just un plus acting on v. So if in this polynomial you have non-constant term, right, then it will kill v, just because v is killed by n plus. So the only thing that I can choose here is just 1, right? So, but h, this one I also can erase. Why? Because h acting on v just multiplies it by a number. Okay? Since this is some algebra, it doesn't. It's just some set, so doesn't really. I can hide number in here, right? Still. So therefore, I can write it like this: un minus v. Okay. But look at this thing. So this thing is spanned by vectors of the form p times v, where p is some monomial right, of the form some f1, f2, and so on, like fk, where these are elements of n minus. Okay. But we know that applying f's, right, I actually, I actually can say it more clearly. I can say in f alphas, right, as alpha is a positive root, right? So actually, this is yes. So so every element in here, un minus, is is a linear combination of monomials in F alphas, right? Because these F alphas, they exactly as alpha run over R plus gives me basis in N minus. Okay, so all monomials, like ordered monomials, in such elements gives me basis in UN minus. But then I apply it to V, and what happens? So V had weight lambda, but when I apply F's, I subtract alphas according to this, right? So therefore, I make a conclusion that V is spanned by weight vectors. So each vector like this is weight vector. So V was a weight vector. When I apply F, it was also a weight vector, but of some different weight, which is smaller than lambda. Okay. So so V is spanned by weight vectors. Of weights some mu which are smaller or equal than lambda. So this exactly means what I would like to prove. Well, of course this means, okay, again, strictly speaking, that means that V is maybe not a direct sum, right? But some sum of weight subspaces. As mu less or equal than lambda. But, right, so every vector here, right, is a sum of weight vectors. So I have, so V is spanned by weight vectors. So it's exactly what's written here. But I need direct sum, right? But this is just this just follows from linear algebra that two vectors of different ways, or like just a bunch of vectors of different ways, they are linearly independent. Because this is again I refer to linear algebra. So then I claim that, so if I have a bunch of vectors and VI's, so these are vectors, or YL, I don't know. It should be V right here. And maybe over there as well. So we started with L. Yeah, I am starting to confuse L and V. So let's keep the notation that we started here. Okay, L, so therefore everything should be L. So this is L. This is L. Yes, and this should be L. L, L, everywhere L. So then I claim the following. It's a purely linear algebra statement. And if you don't believe me immediately, I offer you to check it. You try to prove it yourself. If not, just let me know and we'll prove it together. So I claim that if I have a bunch of vectors in my L, and say V1, Vi isn't, so these are all weight vectors. And also mu I is not equal to mu j for I not equal to j. So suppose that you have this situation. Then I claim that V1, Vk are linearly independent. So this is some linear algebra, but I will leave it as exercise. So therefore, this sum is actually direct sum. So therefore, L is direct sum over L mus as mu less or equal than lambda. Okay. But now, what about part 2? Lambda is a unique highest weight. So suppose you have another highest weight, say lambda tilde. All right? So proof for part 2. So suppose lambda tilde is another highest weight. In L. Then using part 1, we know that L is direct sum of L mus as mu less or equal than lambda tilde, right? But then one of these mu's is lambda. Right, because lambda is a weight in L, right? So therefore, it should belong to one of these mu's. So therefore, lambda is less or equal than lambda tilde. But also, just a similar argument, lambda tilde is less or equal than lambda. But then they coincide. So therefore, if I have highest weight, then it's unique. So this is an important observation. It's an easy but important observation because we would like to classify all irreducible representations, finite dimensional, and they are all of highest weight. Okay. So let us go further. And next step is to consider one particular example, very important, of highest weight representation. It is Verma modules. Okay. Do you remember what was Verma modules from? Okay, some people remember, somebody maybe not. So I will allow myself to give. Okay, so here's the definition. So first of all, of course, U of G is a module, or is some infinite dimensional G module. G module and representation of G is the same thing. Okay, so I can. So usually it's historically that happened that Verma it's called Verma module, not Verma representation, right? So in our literature, you will see the word module. So so U of G is also G module. How this? Why is this? So U of G. So note, U of G is a representation of G. Why is this? Because U of G is the representation of U of G, right? Any associative algebra has what's called a regular representation. It acts by itself on itself by multiplication from the left. Okay. So U of G acts on itself by multiplication from the left. So therefore, u of g is u of g module, right? But we learned that u of g representations of u of g and representations of g, they are the same thing. So actually, our first motivation to construct universal enveloping is to construct associative algebra, which is like the largest possible, which contains as a Lie subalgebra the Lie algebra that we started with. Okay, so representations of u of g and representations of g are the same thing. So therefore, u of g is a representation of g. So this you just take element of g, think of it as an element of u of g, and multiply from the left. So that's the only thing that happens here. Okay, but then we can consider, so any ideal, like an associative algebra ideal, in here, moreover, any left ideal is a subrepresentation. So we can quotient by this subrepresentation. So by definition, the module m lambda, which is u of g quotient by, okay, so let me write it like a scary formula, but we'll understand what it means. So it's u of g h minus lambda of h, sum over h from h, and plus u of g n plus. Okay. So this thing. So first of all, this is left. So in associative algebra, you can have ideals, like left ideals and right ideals. So left ideals is that if you multiply by some elements of u of g from the left, you're still in this ideal. Okay. So this is a left ideal, and it is generated by, sorry, one more parenthesis here. It is generated by all these elements, where H is in Cartan subalgebra, and by all elements of n plus. Okay. In other words, I'm saying that this is as a set. This is a linear combination of all monomials, where on the right I have either element of n plus or elements of such sort. Okay. All, and then on the it is multiplied from the left by any element of u of g. Okay. And of course, if I take some element of g and start multiplying, like start applying, start acting, right, which means just left multiplication, I will still be in this subspace, right, because I multiply from the left something, right? So this is sub-representation. This is an ideal, left ideal, and sub-representation in here. So therefore, this quotient by this is some other representation of G. And we call it M lambda. So this is called Verma module. So let me, so this is the highest weight module. Why? So first let us notice that it is highest weight model, and then we'll see simple example on SL2, just to refresh what was going on last time. So let me take a 1 inside U of G, right? So U of G is unital algebra. It has 1, and then degree 1 elements are G, and then you have like some products of elements of G. So these are higher degree elements, but you have 1 in there, and you can generate the whole representation of U of G just applying, just multiplying this 1 from the left by any elements of U of G. Of course, this is tautology, right? But for us, it means that 1 is a generating vector in U of G, right? You can take this vector and apply U of G to it from the left and get the whole U of G, right? But then if I take this 1 and consider its projection to M lambda, its image, right? So I can take U of G, and this is some quotient. So I have natural projection from U of G to M of lambda. So in M lambda, I will get some vector V lambda. So what are the properties of this V lambda? So now if I take n plus, and well, maybe some element E in n plus, and apply it to V lambda. Okay, so then what it means? It means that I have n plus, right, applied to, right, if I apply it to E V lambda, is the same as that I am applying it to U of G first, right? So how do I act on a quotient, right? I act on any representative, right? And then take quotient. So representative of V lambda was 1. So it means that I take E, apply it to 1, and then take quotient, right? But E is n inside n plus, right? So therefore, when I take quotient, I just kill this, right? So therefore, this is just 0. This is for any element in n plus. Now let me take now some h from Cartan. If I apply h to V lambda, then what's going on? I take h applied to 1, right? But this is modular elements of such sort is the same as lambda of h applied to 1, right? So maybe this is all loosely speaking, right? What the formula that the formula is like this, right? So that's what I'm trying to say, right? Because I claim that all these elements h minus lambda of h, right, multiplying by whatever from the left, they are 0. Okay, so because so informal explanation is that because h applied to 1 equals to lambda of h applied to 1 modulo elements from this ideal. Let's call it, I don't know, J. So this is informal explanation why this is true, but I don't know. It's kind of all here, right? So we say it's just it's just enforcing these two conditions by hand. That's what it is, right? By factoring by this, I'm enforcing this condition. By factoring by this, I'm saying that my 1 now becomes a weight vector. So that's it. Very well. So, and also, since the whole U of G is applied, is obtained from 1, then the whole M lambda is obtained from V lambda by applying V of G, right? So also, of course, the whole M lambda is U of G applied to V lambda, right? So therefore, M lambda is a highest weight representation. So for you to understand better what's going on, we might actually see what is the picture for SL2. This picture we also saw last semester, but it was like in the end, and not a lot of people actually attended. So let's recall what was going on. So for SL2, what all this means. So I choose. So my V lambda is some vector, and then the only so n minus is one-dimensional, right? So f is the only so for SL2. So n minus is just spanned by f, right? And so you take V lambda, you cannot act by E. H acting on V lambda gives you just multiplication by lambda. But then you can act by f, of course. And so you just do it. And you do it infinitely many times. You just apply. So all in your M lambda, it's actually by Poincare-Bergoff theorem again. It's of the same size as UN minus, right? Because again, so this is some observation that should be done like separately, but again, in this example, so that's what is going on. So this is your Verma module for SL2. So it's just some highest weight V lambda, and then you act by f infinitely many times. So it's an infinite dimensional representation. And it's given like this. So this has weight lambda, this is lambda minus 2, lambda minus 3, and so on. And the whole idea was to actually obtain somehow from these infinite dimensional representations finite dimensional reducible representations. Okay? And so the whole idea is that if my lambda now becomes positive integer, then Verma module becomes reducible, and it will have like a, so here I have negative lambda, but then in Verma module, so in finite dimensional representation, I stop here, right? But in Verma model, I can go further down. So this is still not 0 in Verma module. But the idea is that actually, if lambda is so this is negative lambda minus 1, right? Already here. The idea is that if
Minus 1, minus 2.
minus 2, sure, yes. And minus 4 here, yes. Very well. So the idea here is that if your lambda is positive integer, then this is another singular vector. And this is sub-representation then, which you can factor out and get the finite dimensional reducible. So that's how it was constructed for SL2. But this is the picture in SL2. Like in SL3. So remember, you had two simple roots. This one is not simple. And then, so this is the root system for SL3, right? And you had alpha 1, alpha 2. And so Verma module for SL3, you just start with some V lambda again. And then you act by f's. So you act here. And this is negative alpha 1s, right? Like this. And to infinity. And by negative alpha 2s. But also you can subtract alpha 3 as well, which is alpha 1 plus alpha 2. So we get these points inside this fan here. So all these points, they are weights in Verma module. So this is negative alpha 3. But also they have some, so these are weight subspaces. Each point here is corresponds to some weight, and the corresponding weight subspace has some dimensions. So it's actually interesting problem how to compute these dimensions. And we did it, but maybe it's a good way to recall it, maybe on next seminar. Okay. So this is Verma module for SL3. And actually that's for any root system is just like this infinite convex area in which you have some discrete subset, right? Which is just given by subtracting roots from the highest weight vector. So that's your Verma module. Yes.
I'm sorry. Do I understand it correctly that the weight here is calculated like the sum of coefficients in decomposition of the root into symbol?
Weight of what?
Of
So you start Verma module. You start with just any element of H star. It might not be in weight lattice. For SL2, for example, this might be just any number. It might be negative. It might be any complex number. Okay, but to get actually like finite dimensional representation, like to get this special single vector, you just need it to be like an integer.
Okay, that's probably something I missed from the previous semester because like in my head the weight is sum of discrete coefficients.
So weight is an element of vector space.
Yes.
So an element of vector space becomes a tuple of numbers once you fix a basis. Now that's up to you what good basis you would like to fix. That's like next discussion. But your weight in SL2 case, your weight is is a vector in one-dimensional space, so it's actually a number. Okay, so what you're saying that okay, yes, weight is an element of vector space, just an abstract vector space. Once you fix a basis, right, you decompose your vector in this basis, look at the coefficients, and this will be number in like a tuple, like a sequence of numbers, which you call weight. But then that's like a more explicit way of looking at it, right? Vector is not a bunch of numbers, right? Vector is an element of vector space. That's how mathematicians look at it. It becomes a bunch of numbers, or like look at coefficients, once you fix a basis. But you have a bunch of bases here.
What he means the height of a root. He wants to say height of a root is the same as the weight.
Height of root is not the same of weight.
Yes.
Like, I mean, how do you define the highest weight?
I define it like this. So I start with the representation, right? So highest in this sense of this partial order that I introduced. So highest weight, in a sense, is a weight such that there is no in my representation there is no other weight which I can obtain from this one by adding positive roots. So that's my definition.
But isn't it the same as like the sum of all?
No. You can have two roots of the same height, but they're not comparable, for example. They are not obtained one from another by subtracting or adding a positive root. So this order is partial. It's not a total order. It's not all roots are comparable. So yeah. Okay. So very well. Let us go further. Of course, Fermat modules is a good example and very natural of highest weight modules. But then let us apply them at least. So proposition let L be a representation of highest weight lambda. And I don't claim lambda to be in weight lattice or in positive main Weyl chamber, nothing like that. Then I claim that L is actually a quotient of a Fermat module by some submodule. So this is some universal property of Fermat modules, is that you always have surjective homomorphism from Fermat module to any highest weight vector module. And another technical observation that I will need in the future is that this W admits weight decomposition as well. So W is actually sum of W of mu, and moreover, this mu is of course less or equal than lambda. So let us prove this. Yes. Well, proof of part 1 is easy. I'm just claiming that we have a surjective homomorphism from m lambda to L. It sends v lambda, highest weight vector in here, to, well, w lambda, which is highest weight vector in L.
Sorry, the mu should be strictly less or less.
Okay. If you add a non-zero representation, then strictly. Right.
I think there is only one-dimensional.
Yes. Well, you can kill everything. I don't know. It depends on the stupid conventions. Do you know that? Do you want zero space to be a representation of L or not? Of course, you can kill m lambda by factoring by m lambda, of course. Yeah, but I never said anything incorrectly, right? When less or equal, includes less there. Because I never said that w of mu for each mu in here should be non-zero. For w of lambda might be in majority of cases this will be zero. It will not include the highest weight vector. Otherwise, my L is zero. Yes. So when I say that I send highest weight vector here to highest weight vector here, I actually already gave you a map, a homomorphism. Why is that? Because then every vector from here is just an element from u of g times v lambda. Right. So take any for any v in m lambda. Right. V is actually some a applied to v lambda, where a is an element of u of g. Right. But then, if I'm saying that this is homomorphism phi, then it should respect an action of u of g, and the only way, therefore, we already fixed where it should send v. So it's phi of v is phi of a v of lambda. So therefore, it should be a phi of v lambda, and this is just a w lambda, right? So just by fixing where this goes, we already fixed the homomorphism, right? And then, indeed, it is surjective because, again, every w in L lambda, it is, so for every w, we have w is a, or I don't know, let us call b, w lambda. But this is of course in the image of phi, right? Because b of w lambda is phi of b v lambda. Just because, again, phi respects multiplication by u of g. So it's surjective, and then right. So this is the map. We actually right. So we give some prescription. We need to still check that it is well defined. So for example, if I have some relation for vectors in V, in M lambda, right? Then phi should respect this relation, right? But some relation for vectors in M lambda is constructed in such a way that it is isomorphic as a vector space to U of n minus, right? By Poincare-Berkoff theorem, right? You have corresponding bases there, right? And as a vector space, M lambda is isomorphic to U of n minus. So therefore, if I have some relation in M lambda, it is actually a relation in universal enveloping of G, which should also be here because L is a representation of U of G, right? So phi respects relations. So therefore, it's a well-defined map. It's a homomorphism of Lie algebras, and it's surjective because of what I wrote. So I constructed everything. So we proved that L is a quotient of M lambda by something. Okay. Let's prove that W, which is kernel of phi, admits weight decomposition. So consider some W in W. Well, W is not very good because it's also a Weyl group, but I hope no confusion arises here. So this is, specifically in this proof, it's a kernel of phi. Very well. So it's a kernel of phi, but it's an element in M lambda, right? So kernel of phi, of course, is subset in M lambda. But then, since M lambda is the highest weight module, we know that it admits weight decomposition, right? So therefore, W is decomposes as the sum of weight vectors. Where W mu I is inside M lambda of some mu I. Okay, for some mu1, mu I, and they're less or equal than lambda, right? So it is enough to prove that each W mu I is inside the kernel, right? Then I'm done. This will exactly mean that every W is presented as a sum of elements from these subspaces. Okay, and the sum is direct because again this linear algebra reasons. Okay, but very well. Let us take. So let us consider pi lambda. It is the projection from M lambda to L. It's a projection from M lambda to L, which is this, right? Wait a minute, it's the same as phi, right? So maybe I don't need to cook up a new letter for this. Okay, so let us have phi. So if I apply phi to W, then it is 0 because phi is W is inside the kernel. On the other hand, it is phi of W of mu1 plus phi of W of mu2 plus and so on, phi of W of mu k. Moreover, phi, since it's a homomorphism of representations, respects It sends weight vector to weight vector. Okay? So therefore this belongs to L mu 1, this belongs to L mu 2, and so on. This belongs to L mu k. Right? So, but we know that L decomposes as a direct sum of L mu's, right? And each element here is from different summand, right? And this sum is 0. So therefore each element should be 0. So direct. So therefore phi of Wm mu I equals to 0 for every I from 1 to k. So therefore W of mu I is 0, and we are done.